Hello. In this topic, I'm trying to cover RSA encryption algorithm. For start, let's have an overview to our previous discussion. Okay, as I said, there are two kinds of cryptographic algorithms. One group is symmetric cryptography, in which both sides, the sender and the receiver, both have the same key. Okay, there's just one key. Both sides, sender and the receiver, both have the same key. In this picture, you can see that Bob wants to send a message. For example, hello Alice. Okay, Bob encrypts the message using his key. Encrypted message is sent through the network. Alice receives the encrypted message, and now Alice decrypts the message by her key, which is a copy of Bob's key. Okay, so both keys are the same. This is symmetric cryptography. As I said, it's old, and today most of the cryptocurrencies are using asymmetric cryptographic algorithms. In asymmetric cryptographic algorithms, each person in the network has two kinds of key. One, public key. The second, private key. Public is public, it's publicly available. Everybody knows others' public key. For example, Alice knows what is Bob's public key. Eve knows what is Bob's public key. I know what is Bob's public key. Everybody in the network knows the public key of others. But private key is a personal key, is a secure key. Okay. Only one person knows the private key. So everybody knows only his or her private key. This is called asymmetric cryptography. See this figure? Okay. In this figure, as you can see, Bob encrypts her message by his private key. Send it to the network, and now Alice can decrypt the message by Bob's public key. Okay, it's not encryption. This usage, in fact, is authentication. We use this kind of encryption, decryption as a mechanism for authentication. Why it's not encryption? Because everybody in the network knows the Bob's public key. So others in the network also can decrypt this message. So in this case, the message itself is not secure. It's not important that others know what's the message, because others can decrypt the message by Bob's public key. As I said, everybody knows what is Bob's public key. Okay, but this is called digital signature. In fact, since only Bob knows his private key, by encrypting the message with his private key, in fact, Bob signs this message. It's digital signature, and others assured that, oh, it's Bob. When they receive the encrypted message after decryption by the Bob's public key, now they are sure that it's Bob. So it's a kind of authentication. It's called digital signature. Okay. Another usage of asymmetric cryptography, in fact, again, public key and private key, is encryption. Now, Bob once sent the message, for example, hello Alice, and Bob wants to encrypt the message in a way that only Alice can decrypt the message. In this case, Bob encrypts the message with Alice's public key and send it through the network. The only person who can decrypt the message is Alice, because Alice only knows what is her private key. Please note, public and private keys undoes each other, okay? If I lock a message with the public key, I should use private key to unlock it, or vice versa. If I use private key to lock a message, I must use public key to unlock the message. Now, since in this case, Bob wants to prevent others from knowing the message, from seeing the message, he simply encrypts the message by Alice's public key, send it through the network to the Alice. When Alice receives the message, uses his private, her private key, and simply decrypt the message, and it's a usage which is called encryption. Encryption, decryption. Okay. And the third case, third usage of asymmetric cryptographic algorithms is both authentication and encryption, combination of digital signature and encryption. In this case, Bob wants to send a message to the Alice. Not only he wants to Alice be sure that the sender is Bob, in fact, authentication, but also Bob wants the others can't see the message, can't read the message. Okay? So in this case, Bob at first encrypts the message by his private key. Then again, the encrypted message is encrypted again by the Alice's public key. So 2 times encryption. At first, we have an encryption with the Bob's private key. Okay. So everybody who has the Bob's public key can simply decrypt the message, but Bob now doesn't send this message. Before, he encrypts the message again, this time by Alice's public key. Then send this 2 2 times encrypted message through the network to the Alice. Okay? Suppose that Eve now receives the message and wants to spy Alice and Bob. He can't, because the last time the message was encrypted by Alice's public key. To unlock this message, we need Alice's private key, and the only person who has the private key is Alice. So others, like Eve, cannot unlock the message. Okay, now Alice receives the message, unlock the message at first by her private key, then again decrypts the message by Bob's public key. So Bob at first encrypt the message with his private key in the first step, and in the second step encrypts with the Alice's public key. When Alice receives, at first Alice uses her private key to unlock, and then again she uses Bob's public key to decrypt the message, and now she can read the message. So this application is both authentication and encryption. Okay, and this is asymmetric cryptography. There are different asymmetric algorithms. 2 most famous are RSA and elliptical curve. Most of the cryptocurrencies are using elliptical curve. However, in this chapter, we are talking about both RSA and elliptical curve. Okay, now we are ready to talk about RSA. Like cryptographic hash functions, encryption-decryption algorithms or encryption algorithms also one-way function. One-way function means calculation, for example, encryption of a message. It's simple, but without the necessary keys, it's very hard or even impossible to find the input from the output, like hash functions. Using an algorithm like SHA-1, for example, you can simply hash everything you want. But it's very difficult or even impossible to find the source message from a hashed message. Okay, and one-way function means that, for example, RSA also is a one-way function. Why? You can see now. Okay, suppose that Alice wants to send Bob a message and she wants nobody else can read it. So, as I said, Bob must encrypt the message and send it to Alice. But how? Again, as I said, if Alice wants to send a message, so she must lock the message with Bob's public key, and now after that, Bob can unlock the message with his private key. The public key has to be easy to use. Everybody knows others' public key. It's a function easy to compute. But the private key has to undo the public key. It has to be hard to compute. Only the owner can undo the public key. So we need a function easy to compute but hard to compute the inverse. This is called the one-way function. Okay, let's talk about RSA. RSA is based on multiplying large primes numbers. 3%, West, Shamir and Abelson invented this algorithm. So RSA is the first character of their families. So suppose we have two large prime numbers, for example P and Q. It's easy to multiply P by Q. Very simple. Okay. Now, given the product PQ, it's hard to work out what P and Q are. We are talking about very, very big prime numbers. For example, a number with 100 digits. Okay? So when you multiply such a two big, very big prime numbers, it's hard to find P and Q from the product. Okay? But how it works? Suppose that I'm Bob. I want to receive a message. So Bob wants to receive a message and Alice is the sender. So at first Bob, who is the receiver, we said everybody in the network must have public and private key. Okay? So if Bob wants to receive a message, he must have a public key. Now I'm thinking about how Bob must choose a public key using RSA algorithm. At first, Bob must choose two large primes P and Q. Then he must compute the product of these two numbers. Let the product be n. So n is equal to P multiplied by Q. Then Bob must compute the Euler's totient function. What's totient function? Totient function is the number of numbers less than n that are relatively prime to n. We call this coprime. The number of numbers which are less than n and are coprime of n. For example, for simplicity, we choose two small numbers for P and Q. P and Q are two large prime numbers, but for simplicity here, I chose only two small but prime numbers. So let P be 3, Q be 11, so n is 33. The product of P and Q in this case is 33. I want to calculate the totient of n. In fact, I want to calculate the totient of 33. The totient is represented by phi. Okay? So phi n is the totient of n. So here you can see all the numbers from 1 to 32. All the numbers which are less than n. 1, 2, 3, blah blah, 32. Okay? Which are relatively prime to n. What was n? N was 33. 33. Which of these numbers are prime or not prime in related to n? In fact, I want to find the coprimes of 33. It's obvious that 3 is not coprime of 33 because 33 is the product of 3 and 11. So 3 and 33 are not coprime. So I eliminate 3. Not only 3, but also 6, 9, 12, 15, 18, 21, 24, 27, and 30, because all have three as an element. Okay, so if I eliminate all the numbers that are not coprime, these numbers will be remained 1, 2, 4, 5, 7. For example, 7 has no common element with 33. Okay, so 7 and 33 both are coprime. Anyway, we should find the number of coprimes. Coprimes of 33, in this case, it's, if you count them, 1, 2, 3, the number is 20. So the totient of 33 is 20, or phi of 33 is 20. We don't need, in general, we don't need counting like this. There is a very, very simple formula. If P and Q are both primes, then totient P product Q is equal to P minus 1 multiplied by Q minus 1. So totient of 33 is totient of 3 multiplied by 11, and it's equal to 3 minus 1 multiplied by 11 minus 1, and it's 20. Okay, so totient of 33 is 20. So we have P3, which is 3, we have Q, which is 11 in this case, we have N, which is 33, and now we have a totient of 33, which is 20. Okay, and now Bob must choose another number called E. E must be relatively prime to totient of N. A popular choice for E is 2 to the power 16 minus 1. But for simplicity again, in this case, I use 3. So E is 3, because the totient of N in this case is 20, and 3 is relatively prime to 20. So there are many numbers. There are many numbers that you can choose in this state. For simplicity, I choose 3, a number which is less than N and is coprime of totient of N. Okay, so P is 3, Q is 11, N is 33, totient of N is 20, and now we choose E as 3. Now we have a public key. The pair NE is the Bob's public key. So Alice can use this public key to encrypt a message and send it to the Bob. And also, please note that totient of N without having P and Q is very hard to compute. And now we have a public key. Public key in RSA algorithm is a pair. Okay, in our case 33 and 3. So our public key here, in fact Bob's public key here is 33 and 3. We should convert our message to a number. For example, if you want to send a message like hello, you can say, okay, at first I encrypt H, then I encrypt E, then I encrypt the first L, then the second L, and finally O. For encrypting the H, you can simply use its ASCII code. It's just simple solution. Okay. However, with some approaches, we convert our message to a number or some numbers. And now let's see how we can encrypt one number. Suppose that Alice's message is turned into a number like 15. And now I want to encrypt 15. For encryption, we use this formula. In fact, the cipher text C is equal to M. What is M? M is our message, the number. Okay, M in this case is 15. M to the power of E mod N. We use this formula to encrypt the message. So in this case, 15 to the power of 3 mod 33, because N in this case, as I said, is 33. Mod 333 is 9. So the cipher text or the encrypted message is 9. So I explained how RSA finds the public key. Then, using this formula, everyone who wants to send a message use this formula to encrypt the message using the public key. The pair N and E is the public key. Okay, the only thing that now I must explain is how to decrypt the message. Now, okay, now Alice sends this encrypted message 9 in this case, and now how Bob can decrypt the message. I must explain two things. At first, how Bob must choose a private key. For the public key, it's okay, we saw that. And now I must explain how Bob defines his private key, and after that, by which formula Bob can decrypt the message. Okay? For the private key, Bob must choose another number, D. Bob must choose another number, D, in a way that D multiplied by E must be equal to 1 mod totient of N. In this case, the totient of N is 20. So, please note, Bob is the person who chose P and Q. So, since he chose P and Q, so he knows what's totient of PQ, he knows what is E, so he can simply find a number like D in a way that D multiplied by E is equal to 1 mod totient of N, or in this case 1 mod 20. Since 7 multiplied by 3 is equal to 21, and 21 mod 20 is 1, so we can simply use 7 as a value for D. So D, suppose that D is 7 in this case. And now, the pair N and D, in fact D is the private key. So D is the private key, and now Bob must use D and N to decrypt the message. How? With this formula. As we saw that we use this formula to encrypt the message. So C is the ciphertext, the encrypted message. The encrypted message was 9, and now unciphered, the unciphered message U, the formula is here, is equal to ciphertext to the power D mod N. We use this formula to decrypt. So our ciphertext was 9, so 9 to the power 7 mod 33 is 15. And as you know, 15 was our original message. Maybe you ask, why does it work? It's mathematics. You can simply find some proofs that mathematically proves that these formulas work. Okay, so it was. Let's look at another example. In my example this time, I consider P as 23, Q as 19, N will be P dot Q, which is equal to 437. Okay? And now the torsion phi of n is 22 multiplied by 18, which is 396. Okay? And now, as a public key, I must choose E in a way that it's a coprime of torsion of phi. For simplicity, I choose E as 5. Please note, in reality, it must be a very big number. All these numbers must be as complex as possible because we don't want others to guess our keys. Public key is not important because we announce the public key, but private key is very important. Okay, now if I want, suppose that my message is 121. If I encrypt the message, so the cipher text C is equal to M to the power E mod N. So in this case, 121 to the power 5 mod 437 will be 163. You can simply check. Okay, now to decrypt, we must have the private key. As I said, we must choose the private key D in a way that D multiplied by E be equal to 1 mod torsion of N. If we choose D as 317 multiplied by 5 is equal to 1 mod 396. So to decode the message, now we should use the decryption algorithm. If you do so, the ciphertext is 163. Okay, so the ciphertext is 117 to the power of D. D is 163 to the power of D. D is 317 mod just a second please. Mod N. So n in this case was 437, and if you calculate the result of this formula, we must receive to 121. Okay. This was RSA. I ignore the proof of RSA. We just want to use it. So this is the RSA. There are different implementations. I will show you one of the implementations in Python for encryption, decryption, digital signature verification. Also, there are different online calculator for RSA algorithm. You can simply search RSA online calculator. There are many online calculators that you can generate public key, private key by them, and you can use those public and private keys to encrypt, decrypt, and creating digital signatures. In the next session, in the next lecture, I will show you how to use them in the programming languages, especially in Python, and also we will see how those online calculators work. Okay, that's it for now. See you. Bye bye.